Hello all, welcome to chapter 7. So in this chapter we'll enter into the topic of organic chemistry and the reactions. So in this lecture we'll discuss alkyl halides and we'll talk about nucleophilic substitution and elimination reactions. So this is the first time you're going to learn more about organic chemistry in terms of the reaction mechanisms. So let's start with this lecture. So in this lecture we'll talk about introduction to substitution and elimination reactions. We'll also talk about nomenclature and the uses of alkyl halides. We'll talk about a specific type of substitution reaction called nucleophilic substitution reaction. And we'll talk about nucleophilic strength and the solvent effects in SN2 reactions and SN2 reactions in biological systems. And then we'll enter into E2 reactions, which are basically called elimination reactions. And we'll discuss the formation of alkanes. And we'll talk about regiochemical and stereochemical outcomes of E2. And we'll also discuss unimolecular reactions, which are the second type of substitution reactions and elimination, which is SN1 and E1. And we'll talk about kinetic isotope effects in elimination reactions, and we'll try to predict products between substitution and elimination. And we'll also talk about substitution elimination reactions with other substrates, and finally end with synthesis strategies. In the first lecture, we'll discuss, so let's start with the first part, introduction to alkyl halides. So alkyl halides are the common compounds that undergo substitution and elimination reactions. So whenever you see a compound, for example, in all the compounds that you see here, you see three different types of hybridizations. All of these compounds come under the classification of halides, but in each of these highlighted carbon here, we know that one only represents alkyl halide because it is the sp3 hybridized carbon atom. So the one with the sp3 hybridization is the one that ends up becoming the alkyl halide, because that is the one that undergoes the reaction. So alkyl halides can undergo substitution and reactions when you react it with a nucleophile. So in the last lecture we talked about a nucleophile. A nucleophile is a molecule that is electron rich and is ready to donate electrons to form a bond. So substitution reactions involve a nucleophile replacing the halogen and attaching itself to the carbon atom by making sure that the halogen leaves the structure. Elimination involves a base, generally resulting in the compound basically leaving the base. So the base tries to push the halogen out, and it also snatches one of the protons on the structure, resulting in hydrogen base structure, and finally leaving the leaving group eventually leaves and resulting in the formation of an alkene. So elimination reactions are commonly compounds that result in alkene formation. In substitution reactions, you are basically substituting the halogen with the nucleophile. So what do nucleophiles and bases have in common? The only thing that the base have in common is being electron rich. Bases in general should be atoms that should have at least one electron pair and a negative charge. Nucleophiles need not be always structures that should have a charge. They can be structures that cannot have a charge as well. So when a reagent can act as a nucleophile or a base, depending on what way it acts, it can have elimination and substitution that compete between the reaction pathways. So it can act sometimes as an elimination product, or you can end up getting an elimination product or a substitution product, depending on the reagent that you use. So in the above example here, which compound is the substrate? The substrate is the product that you end up with that becomes both the combination of elimination and substitution product. Now there are two main reasons why alkyl halides are the ones that generally undergo substitution and elimination reactions. Number one is halogen here is an electron withdrawing group, and because it's an electron withdrawing group, it creates a partial negative charge on the halogen and a partial positive charge on the carbon, leading the nucleophile to attack the positively charged carbon. And because the halogen has higher electronegativity than carbon, it acts as a leaving group, and for the substrate to undergo substitution elimination reactions, this is the main important point. For any substrate to form a substitution or elimination reaction, undergo a substitution or elimination reaction, the product, the halogen here that you use must be a very good leaving group. Unless it's a good leaving group, this reaction will not occur. So what are good leaving groups? Most commonly good leaving groups are conjugate bases of strong acids. For example, if you take Br minus is a good leaving group because HBr is a strong acid. HCl minus is a good leaving group because HCl is a strong acid. So the conjugate bases of strong acids are the most common good leaving groups. So for example, if you take H2O or alcohols, these are generally bad leaving groups, and amines are the worst of all leaving groups. And the best of all are the halogens and sulfonate. So sulfonates and water are the best leaving groups, good leaving groups. Now, alkyl halides are generally compounds where you have a carbon atom that is bonded to a halogen. The halogen here can be fluorine, chlorine, bromine, or iodine. Now, recall the naming component here. The halide group here is the key substituent, and we will name it and locate that particular halogen. For example, here the chlorine here is in the second carbon, so we can name it 2-chloropropane. There's 3 carbons, and you have 5 carbons here and a bromine on the second carbon, so 2-bromo, 2-methyl pentane. In the same way, if it has chirality, then we base it on the chirality of the compound. For example, here the chirality here results in R structure, and you get R fribromo 2,3,3 trimethyl heptane. So the naming nomenclature stays the same. Now, so we can make some simple molecules can also be recognized by their common names. The common name given to it is based on the halogen. For example, you can name a compound haloalkane depending on the halo and the alkane. So for example, chloroethane is the common name given to ethyl chloride. This is the common name that we use as well. So systematic name is chloroethane. Ethyl chloride is the common name that you can use. So dihaloalkane, here we can write it as dichloromethane. Here the other name is methylene chloride, which is another common name for this structure. So pause the video right here and try to name these structures. Next, let's talk about the structure of alkyl halides. So we use Greek letters to often label the carbons that are attached to carbons to the alkyl group attached to the carbon. So the alkyl group that is attached to the carbon that is attached to the alkyl, the halogen, we call it the alpha carbon. The carbon adjacent to the alpha carbon, we call it beta carbon. The carbon adjacent to the beta carbon, we call it gamma carbon. Now the amount of branching here at the alpha carbon affects the reaction mechanism. So with this condition, there can be 3 types of alkyl halides: primary alkyl halides, secondary alkyl halides, and tertiary alkyl halides. So the alkyl halides nomenclature comes from the base of the number of substituent groups attached to the alpha carbon. So if there is one substituent group attached to the alpha carbon, we call it primary alkyl halide. If there are 2 substituent groups, then secondary. If there are 3 substituent groups, tertiary. So this is how we name the structure. Now, some alkyl halides are commonly used as insecticides, and one of the common ones is DDT and lindane. DDT is the original compound that is used to kill mosquitoes, and mostly it comes in the form of a foggy spray. Lindane is another compound that's used commonly as a insecticide as well. Now, halides appear in a wide variety of natural products and synthetic compounds. For example, the structure and of the molecule is basically determines its function, and the functions commonly include things like insecticides, dyes, drugs, food additives, and many more. So some of the most common drugs like anti-cancer medication, antidepressants, antimicrobial compounds all use organohalides as a part of their structure. Now let's come to the first type of reactions, SN2 reactions. Now a substitution reaction requires, we already talked about this, a loss of a leaving group and a nucleophilic attack. Now there are 2 ways in which these reactions can occur. One is a concerted mechanism, and the second is a stepwise mechanism. In a concerted mechanism, it involves breaking of the bond to the leaving group and making of the bond to the nucleophile at the exact same time. Notice that both of them are happening simultaneously, If both happen simultaneously, we call that a concerted mechanism. If both take two steps, for example, first it loses the leaving group and second it undergoes a nucleophilic attack, we call that a stepwise mechanism. In a stepwise mechanism, you actually have an intermediate that is formed, and it is the carbocation intermediate. So this carbocation intermediate is the one that forms, and that carbocation intermediate then undergoes a nucleophilic attack. So this mechanism is called as a stepwise mechanism. The reactions that undergo using the concerted mechanism are called SN2 reactions. The reactions that happen with stepwise mechanism, we call that SN1 mechanism or SN1 reactions. So SN2 reaction here requires concerted substitution, where the nucleophilic attack and the loss of leaving group happen at the exact same time. So where the nucleophile attacks the carbon on the one side and the halogen leaves on the other side, resulting in the formation of the compound at the exact same step, and it happens in one step. So what does S, N and 2 represent here? So notice that here, for the reaction to occur, you need both the nucleophile and the halogen to be present at the same time. That's what 2 stands for here. 2 represents that this is a dimolecular reaction, which means that both reactants are the limiting reagents, limiting reactants. So because unless both of them are present, the reaction cannot occur. That's what limiting reactants basically means. And S here represents substitution, N here represents nucleophilic. So that's the nomenclature base here. So because it has a dimolecular reaction, the rate law here can be written as K times the nucleophile times the halogen. So Hx, let me write it this way. Let me write it as Rx. So this is the rate law for this reaction here. Now, what is the observed stereochemistry in this reaction? So the stereochemistry involves inversion or inversion of configuration. This is a common step in SN2 mechanisms. In SN2 mechanisms, if you started the halogen with an S structure, after the nucleophilic substitution, it changes its structure to R. Why does this happen? Is because the nucleophile attacks from the back side and the halogen leaves from the front side. So the halogen here attacks here, and this halogen, the halogen leaves this way. That's the reason why it undergoes an inversion of the configuration. So this is what we call the backside attack of this structure. So this backside attack, what does it do is it creates a transition state. The transition state involves the formation of this structure here. And on this side we have SH, and on this side we have Br. The reason I am writing it as a dotted line is because this bond is the one that undergoes transition, which means that this is the state where it decides whether to go back towards the R structure or towards the S structure. So what happens now when the reaction fully occurs? This bromine here takes its electrons and leaves the structure, resulting in the formation of this structure where these structures bend towards the side which is much more freer. So resulting in the formation of the transition state. So this is how you draw the transition state. One, the side on which the nucleophile attacks on one side, and the side on which the structure leaves on the other side, making the structure that is there in a single plane. Now, in terms of the kinetics, the less sterically hindered the structure, so the less sterically hindered electrophiles generally react more readily under SN2 conditions. So tertiary halides are generally too hindered to react via SN2 mechanism. So the most reactive one is methyl, and next is primary. Secondary and tertiary are generally much more unreactive in terms of SN2 mechanism. So the alkyl group branching from the alpha and the beta carbons, it basically also hinders the backside attack of the nucleophile, so resulting in the slower rate of the reaction. So which means that if you have the alpha carbon is more hindered, then that means that reduces the relative rate of reaction of the compound. The same thing happens when the beta carbon is also hindered. If the beta carbon is free, then the reaction rate is high. If beta carbon is hindered, the reaction rate is very low. So this here is a diagram that represents the kinetics of an SN2 mechanism. So you start with the mechanism here with the two reactants. The activation point, the activation energy or the peak of the energy diagram represents the transition state, and finally you end up with the product. So this activation energy is the energy required for it to achieve the transition state. For the compound to achieve the transition state is what we call the activation energy. Now, depending on the SN2 reaction, so the activation energy also changes because it's hard to create the transition state when the structure is hindered. When it is hindered completely, when you have a tertiary structure, secondary substrate, the nucleophile cannot readily form the transition state. So that's why it takes a lot of energy to achieve the transition state. For a primary structure, it's much easier, and for methyl, it's the easiest to create the primary structure because it's just surrounded by hydrogens, which are not that big of a compounds to stop a nucleophile from attacking the structure. So tertiary substrates generally react too slowly to have any measurable data of the reaction. So an example to consider is to consider the structure of neopentyl bromide. So try to draw the structure of neopentyl bromide. So neopentyl bromide, you have, so this is a structure of neopentyl bromide. Now, I'm sorry. So this is a structure of neopentyl bromide. Now, this neopentyl bromide here, how would you classify this structure in any manner, and how would you take, is it a primary, is it a secondary, or is it a tertiary alkyl halide? So should neopentyl bromide react by an SN2 mechanism relatively quickly or relatively slowly? So remember that the alpha carbon is what decides the structure, which means that the alpha carbon is much more hidden, which means that this reaction is not going to be occurring easily. Now, what are the factors that contribute to the strength of a nucleophile? So a strong nucleophile is the one that is needed for an SN2 reaction. Remember this principle: unless the nucleophile is strong, the reaction cannot occur. So for SN2 reaction to occur, you need a really strong nucleophile. So for example, OH minus can be considered a good nucleophile. So it attaches itself and the iodine leaves right away. So it's a fast reaction and the reaction will occur. Now the same thing does not happen with water directly, but it is very slow, but the reaction does occur, resulting in the formation of a charge. Remember that if the nucleophile already has a negative charge, it's easy for the reaction to form the product, but for a neutral nucleophile, it's harder and slower to form a product. So be able to recognize that given nucleophile here is whether it is strong or weak. So some of the most common strong nucleophiles are halogens, sulfide, and sulfonates, and you have hydroxyl and alkoxy groups, and you have cyano. These are strong nucleophiles. Anything that is neutral, alcohol groups and water, are examples of weak nucleophiles. So you should be able to determine if the nucleophile is strong or weak and which ones are suitable for SN2 reaction. Remember that anions are generally very strong nucleophiles, and polarizable atoms are also good nucleophiles, and the solvent that you use also affects the nucleophilicity of that particular compound. So for SN2 reactions, what type of solvents do you need? You need a polar aprotic solvent. What is a protic solvent and an aprotic solvent? Protic solvents are solvents that have a proton connected to a polar compound, connected through a polar bond. So aprotic solvents are compounds that can form a hydrogen bond but do not have any accessible protons for them to readily donate. So polar protic solvents engage in hydrogen bonding and stabilize the anionic species. Aprotic solvents stabilize both cations and anions. So how do these factors play in the strength of a nucleophile? The main reason mainly is because of the fact that because it readily donates a proton, it's harder for the reaction to occur. In SN2 reactions, you need to have no involvement of any external structure, so which means that it should readily have a chance to act right away. So if there is a proton, there is a chance that it becomes acidic and the nucleophile does not have the chance to donate its electron pair. So the nucleophiles are generally less stable, thus more reactive in an aprotic solvent. Now the activation energy will lower and the reaction will become faster. So when you use a protic solvent, you need a lot of activation energy, but when you use a aprotic solvent, you require a small amount of energy, because the nucleophiles are generally less stable, and because they are less stable, they become more reactive in aprotic solvents. So remember this, aprotic solvents are the best for SN2 reactions. The common aprotic solvents that you will see are acetone, dimethyl formamide, which is given by its short form DMF, HMPA, which is hexamethyl phosphoramide, DMSO, which is dimethyl sulfoxide, acetonitrile. These are acetone. These are common examples of polar and aprotic solvents. Now, halides are generally common leaving groups for laboratory use, but are not common substrate in biological SN2 reactions. So, to make sure that we create a good leaving group, so both of the compounds here are good methylating reagents. So, a good nucleophile will always attack the CH3 via the SN2 mechanism. So, this is the idea behind SN2 mechanism and how it works. Next, let's discuss the elimination reactions. Let's start with E2 reactions. So, when an alkyl halide is treated with a really strong base, what will happen? So, it undergoes what we call beta elimination. Beta elimination is the process where it undergoes alpha beta elimination. So, it undergoes 1,2 elimination to form an alkene. So, what happens in this reaction? So, you have the alpha carbon which is connected to the halogen and a beta carbon that's connected to a proton. What happens here is there are two things that get eliminated. One, the halogen, and two, the proton on the beta carbon. So both get eliminated, and there is a bond formed between the alpha carbon and the beta carbon. So it creates a double bond between the alpha and the beta carbon, resulting in the formation of an alkene. Now, for this reaction to occur, you need a really strong base that will react in a concerted mechanism. Remember that concerted here, meaning that both happens at the same time. So what happens here? The base attacks the proton donates its electrons back to the carbon, and the carbon will leave the halogen to go out of the structure. And all of these happen at the exact same time, resulting in the formation of an alkene. Now, E2 elimination here is a concerted mechanism, which means that you need both the reactions to occur at the same time. So where the base removes the beta proton, causing the loss of leaving group and the formation of the double bond. So this mechanism is also bimolecular, which means that both the alkyl halide and base are needed at the same time for the reaction to occur. So the E here represents elimination and 2 here represents that the reaction is bimolecular, which means that the rate involves both of the compounds here. Now, what difference here is between the SN2 mechanism and the E2 mechanism? In the E2 mechanism, there is both of them. What are the main similarities that you have? One is the loss of leaving group, and the second similarity that you have is that both of them do have a negatively charged atom. Now, the question here is that why does E2 elimination result in elimination, and why does SN2 result in substitution? The reason this depends on the compound and depends on the base that you use. So here, when you use a strong nucleophile, it undergoes substitution reaction. When you use a strong base, it undergoes the elimination reaction. So this is something that you have to remember. Not just because it's a strong base doesn't mean that it's a good nucleophile. So a strong base here is something that is a bad leaving group and a structure that is a strong base. Now the reactions here is the effect of the substrate is substantial on the reaction. Now consider a reagent sodium hydroxide NaOH, which is a strong nucleophile and also a strong base. Now why does it not undergo this reaction easily here? Is because hydroxide here functions as a nucleophile, but when it functions as a nucleophile, the problem here is that the structure is very much hindered, which means that the reaction cannot occur directly. So E2 elimination is generally used when the substrate is sterically hindered, and E2 reactions generally occur in tertiary carbons. So in tertiary alkyl halides, it's most common to see E2 elimination to occur. Now let's go into alkenes and their nomenclature. So alkenes are given IUPAC names on the same procedure as alkanes, but only with minor modifications. Number one is the parent chain must always include the double bond. Number two, identify and name the substituents. Number three, give the carbon double bond the lowest number possible. And number four, list the numbered substituents before the parent name in alphabetical order. This is the same thing. And the last point that you additionally see here is that the carbon double bond locant is placed either just before the parent name or just before the ene suffix. So for example, if it's at the third position, we can call it pent 3-ene, so there are 3-pentene, depending on what the structure is. So this is pentane. If it's on the first carbon, you don't need to write the structure, the locant. You can just write pentene. Now, if the structure involves the double bond, which means that the structure that involves the double bond should become the parent carbon or the parent chain. Now, when you give the number, always give the lowest number to the double bond, even though the substituents are with a larger number. It doesn't matter. Always make sure that the double bond is the one that gets priority over the substituents. Now, if you have the isomerism there, then use the EZ representation depending on the priority of the two groups. If the priority is on the same side, then name it Z. If it's on the opposite sides, name it E. So that's the nomenclature that we generally use. So if the top priority groups are on the cis to each other, Z. If they are the opposite to each other, E. Now, because of steric strain, generally cis isomers are generally less stable than trans isomers, and most of the products that form are always trans isomers. So this is something that you will have to remember. So trans isomers are much more stable because they have lesser energy. The lesser the energy, the more stability that they have. Now, so the more alkyl groups here, the more stable the alkene. So the same thing happens here in terms of the stability. The more substituted the carbons attached to the alkene, the more the stability. So the tetrasubstituted alkenes are the most stable one. Monosubstituted are the least stable of all alkenes. Now in cyclic alkenes with less than 7 carbons, there is only cis alkenes are stable. The reason why is because we do not need to indicate if alkene is cis or trans unless the ring contains 8 or more carbons. So the common rule that we use is called as the Brett rule. So you don't need it right now. The common rule that we use here is most commonly used to bicyclic compounds. For example, this compound here is not a stable compound, but this compound is stable. The reason mainly is because here the structure is cis, here the structure is trans. So this is the idea behind Brett's rule. Now in terms of the regioselectivity here, E2 elimination involves the formation of a double bond, which means we also have to understand which is the alpha carbon and which is the beta carbon. Now that depends on the solvent that you use. If the solvent that you use is a strong base, so if it's a strong base, it always results in a more substituted alkene, which will be the Zaitsev product. The less substituted alkene is called as the Hoffman product, and it is minor product. So if the base that you use is strong base, it forms Zaitsev product more. If you use a weak base, it creates more Hoffman product. So the more the base here is what decides whether the compound is stable, it creates the Hoffman product or the Zaitsev product. Now E2 elimination again is regioselective, which means that the major product will always be the more substituted compound depending on the structure that you use. So this is the main point that you will have to remember. If the base here is ethoxide, it generally creates Zaitsev product more. But if you use a more substituted structure, for example a turbutoxide or any more structures, the more substituted the carbon structure, it results in more and more Hoffman product. So if you use a simple base, it creates the Zaitsev product. If you use a complex base, it creates the Hoffman product. So this is the differences between the two structures. So use that principle now and try to solve these problems. So let me do the first one. you have sodium ethoxide and you have chlorine here. Now you're looking for the more substituted carbon. So this is the alpha carbon and this is the beta carbon. Remember that it should contain a proton. So we'll have to check whether it contains a proton or not. So first thing to look for here is this is the alpha carbon and this is the beta carbon, which means that this is the beta carbon. The beta carbon here already has 4 bonds. It does not have any other . So now here the beta carbon should have a proton. Here there is no protons on this beta carbon, so which means that this will not work. So the only other beta carbon is this one and this one. So which one will end up becoming the carbon depends on the structure that you see here. So here we have an ethoxide, which means that the major product will be the more substituted carbon. So the more substituted carbon is the alpha carbon that has more bonds. Here this carbon is connected to 2 other carbons, but this carbon here is only connected to 1 carbon, which means this carbon becomes the minor product and this carbon becomes the major product. So how would you draw the structure? So just draw the structure and eliminate the chlorine. So you have the double bond here. This structure here represents the major product plus the minor product will be this structure. So here this is the Zeise product and this is the Hoffman product and this is the major product and this is the minor product. So use this principle and try to solve the other 2 problems. Notice that here terbutoxide is a complex structure, which means that Hoffman product will be the major product and the minor product will be the Zeise product. So use the principle now and try to solve this problem. Now, in terms of the stereoselectivity, so when you use elimination structures, the elimination creates both major and minor products. So the reason strand structures are more stable is because they have less energy. That's the reason why they are generally more stable. So in terms of the stereospecificity of E2 reactions, so there is only 1 proton here that undergoes the beta elimination. So this is what we call the elimination here involves the removal of beta hydrogen. So that beta hydrogen should be in the trans direction to that of the halogen. So if both are in the same plane, it undergoes easy elimination. So this here is the idea behind the reaction here. So if both the halogen and the hydrogen are on the same plane, then the reaction will occur easily and it creates the product that it needs to create. So this is the stereospecificity of this reaction. So here the beta hydrogen and the leaving group should be coplanar. So for example, what does the coplanar mean here? Is that when you take and draw the Newman projection, the halogen should be on the top and the hydrogen should be on the bottom. This is the only case where E2 elimination will occur. So this is the only case where the process will occur correctly, and this is how stereospecificity is used in E2 elimination reactions. Now, so whenever we do not have this, what we generally do here is we rotate the carbon-carbon bond, and if they are not coplanar, so if they are anti-coplanar, only then the reaction will occur. If they are syn-coplanar, the reaction does not occur. So the lowest energy rotomer should be the one that has hydrogen on top and bromine on the top. So only then the reaction will occur. So this is the only case where the reaction will occur, and this creates an anti-coplanar rotomer where once the elimination, so what happens here? The proton, the base here attacks the proton donates its electrons back to the carbon and the bromine will leave. This results in the formation of this structure here. This structure is where we end up getting the double bonded, and most commonly E isomer will be the one that forms because it's always trying to make sure that the structure has on both sides. For example, if you look at it here, terbutoxide, here it is phenyl, both are on opposite sides, that's why it creates a E isomer. So evidence suggests that there is a strict 180-degree angle is not necessary for E2 mechanisms. So most common angles that are sufficient is around 175 to 179. So we use the term anti-periplanar that is generally used instead of anti-coplanar to account for the slight deviations of coplanarity. So, but always the E isomer is the one that is more stable because it generally is the one that is less hindered and it requires the least amount of energy to stay stable. So use that principle here. So draw the Newman projection and try to find the reaction here. Try to find the product here. Now for the following substrate here, the beta carbon has 2 beta hydrogens. So which one will be the one that undergoes elimination? Remember that the one that undergoes elimination is the one in the same plane. So this is the same plane. So that's why this is the proton that gets eliminated more often than not. That's the reason why is because the reaction will be stereoselective but not stereospecific. Remember this difference here. Stereospecific means that the reaction only occurs when it is in anti-periplanar position. But stereospecific is only when it chooses a particular proton to remove. So when you have more than one, it chooses the one that's always the one that's easy to remove. So it's very important to understand the term stereospecific and stereoselective. So in a stereospecific reaction, the substrate is stereoisomeric and the results in one stereoisomer as a single product. So you only get one product. In a stereoselective reaction, you get both the 2 products, one major and the other minor. So consider the structure here. Consider the dehydrohalogenation of a cyclohexane derivative. Here the chlorine, when you draw the Newman projection, you will notice that the chlorine and hydrogen are in the same plane, which means that it's easy to undergo the elimination. So which means that here this is a reaction which is stereospecific, which means that this reaction undergoes a specific reaction where this is the only configuration where the E2 elimination will occur, but for this configuration E2 elimination will not occur. So the leaving group should always be in the axial position, not in the equatorial position. So use that principle now and try to draw the projections for these 2 structures and see if you can find out which one will undergo E2 elimination and which one cannot undergo E2 elimination.